So welcome back, aerodynamics class. We will continue our discussion on thin airfoil theory, and before that, we have made it for the symmetrical airfoil, and now we will do it for the cambered airfoil, right? So we will have a small recap. Before that, let us start with the acknowledgement. I acknowledge John D. Anderson's Fundamentals of Aerodynamics, right? So we have started with the thin airfoil theory, and we know this relation, right? This relation is common for every case, whether it is a symmetrical or cambered, and we will utilize the same relation now because for the cambered airfoil. Then we have made assumption that dz by dx becomes 0, right? So once dz by dz becomes 0, dz by dx becomes 0, then it is a symmetrical airfoil, and we have transformed into theta coordinate, and then we have calculated the lift per unit span based on Kutta-Jaworski. Then we calculated the coefficient of lift and the dCl by d alpha, that is lift curve slope, and we have attained the moment also, right? So we end up with the moment, right? Moment calculation, and we had a summary that the Kutta condition satisfied, and the CL is equal to 2 pi alpha. Then the lift curve slope is dCl by d alpha, right? And the dCl by d alpha is equal to 2 pi or otherwise 0.11 per degree, and so on. And also we understand that the center of pressure and the aerodynamic center are located at the quarter chord point in the case of the symmetrical airfoil, right? Now, I will take this same relation which we had taken initially, gamma of zeta d zeta by x minus zeta, and we will continue with the cambered airfoil, right? So for cambered airfoil case, see, please note I derive one by one and I follow John D. Anderson's notation because then only you can follow that with the book and this derivation. So that's why even John D. Anderson refers some other book for different points, but still I use the same notation of John D. Anderson. That will make your derivation and the thinking on aerodynamics easier. So whatever question you have, please post and I will answer, right? So let us start with the thin airfoil theory, cambered airfoil, but the generalized equation 1 over 2 pi integral 0 to c gamma of zeta d zeta by x minus zeta, that is equal to v infinity into alpha minus dz by dx, right? So in the case of cambered airfoil, the dz by dx is finite. In the symmetrical airfoil, we have assumed that dz by dx equal to 0, right? So this equation becomes little elaborate. So I will transform this into theta. Then we can write the same equation as 1 by 2 pi integral 0 to pi gamma of theta sine theta d theta by cos theta minus cos theta naught that is equal to V infinity into alpha minus dz by dx. Right? Now, as usual, we wish to apply, we wish to obtain solution for gamma of theta, and that has a certain condition like gamma of pi should be equal to 0, right? So again, the solution for gamma of theta will make the camber line a streamline of the flow, right? So you remember that we have considered gamma of theta in the symmetrical airfoil, right? Say we have considered gamma of theta. So gamma of theta here, right? And we have made a so we have proved that this satisfies the equation, right? Similarly, for the cambered airfoil, we will have the gamma of theta, and we will just check whether it satisfies, right? So 2V infinity A naught into 1 plus cos theta divided by sin theta plus n is equal to 1 to infinity an sin n theta. Right. So this expression is even a little stronger expression, and the gamma of theta, which we have calculated in the symmetrical airfoil, and this case is little different, right? So we can again prove, we can just substitute the gamma of theta in the above equation, and we can arrive to the solution, right? So the coefficients, we have an. An is the Fourier sine series term, and an depends upon the shape of the camber line, and the a naught depends on both alpha, the angle of attack, and the slope, right? So this a naught, which depends upon the dz by dx and alpha, which is angle of attack, and the an is a Fourier sine series term, right? That depends on dz by dx. So we will come across, right, the coefficients a naught and an can be n is equal to 1, 2, 3, and that must be a specific value in order that the camber line be a streamline of the flow. So to find these values, let us substitute the gamma of theta in the equation here, right? Substitute it in this equation. So let us write there. Now 1 by pi integral 0 to pi a naught into 1 plus cos theta. That sin theta gets cancelled, and I write it directly. A naught into 1 plus cos theta d theta by cos theta minus cos theta naught plus 1 by pi n is equal to 1 to infinity integral 0 to pi an sin n theta sin theta to d theta by cos theta minus cos theta naught, that is equal to alpha minus d z by d alpha. Right? So we cancel that v infinity also. Right? Now we will evaluate the first integral from the standard integral. Right? What is that first integral? The standard integral we already know. So please check, and somebody can say the standard integral. We have integral 0 to pi cos n theta d theta and cos n theta n theta naught by sin theta. Right? So please let me know. So by doing so, we will get this as so this integral, I recommend you to refer your symmetrical airfoil case. And the second integral, I will write the standard integral of 0 to pi sin n theta sin theta d theta by cos theta minus theta naught, that is equal to minus pi cos n theta naught. Cos n theta naught. Sorry. Cos n theta naught. So by substituting the standard integrals, now this equation can be written as, so please substitute and come back. You can write a naught minus n is equal to 1 to infinity a n cos n theta naught, that is equal to alpha minus dz by dx. So the camber line, we need to include the camber line in the equation. That is why we are doing all this discussion, right? So this equation can be written again as dz by dx. Originally, dz by dx is to find the slope of the camber, right? Alpha minus a naught plus n is equal to 1 to infinity a n cos n theta. Right? So here dz by dx is a function of theta naught, right? Dz by dx is a function of theta naught. And we already know that x is equal to c by 2 into 1 minus cos theta naught, right? So we need to calculate a naught and a n, right? So in general, the Fourier cosine series representation of function of theta, right? Say function of theta can be expressed in terms of B naught plus the summation of n is equal to 1 to infinity Bn cos n theta, right? So we can calculate B naught and Bn, right? And then we can calculate A naught and An also. I recommend you to do it by yourself, and I will write the direct equation A naught, that is equal to alpha minus 1 by pi integral 0 to pi dz by dx and d theta naught, and An is equal to 2 by pi integral 0 to pi dz by dx cos 1 theta naught into d theta. So as I said, dz by dx is a function of theta naught, and the A naught depends on both angle of attack alpha and dz by dx, but the An depends only on the slope of the camber line, right? So with this information, we have A naught and An, and hence we can directly calculate the circulation. So let us come back with the equation for circulation. So once we calculate circulation, we can calculate the coefficient of lift. So the total circulation due to the entire vortex sheet from the leading edge to the trailing edge, we can write 0 to C gamma of theta into d theta, that is equal to C by 2 into integral 0 to pi. I transform it into theta, so gamma of theta sine theta d theta. So we already know what is gamma of theta, right? Gamma of theta is equal to 2b infinity into a naught into 1 plus cos theta by sin theta plus summation of n is equal to 1 to infinity an integral 0 to pi sorry, here an sin n theta, right? An sin n theta. So with the gamma of theta, we can calculate the total circulation gamma. So please write the total circulation, that is C into V infinity. We can say A naught into integral 0 to pi 1 plus cos theta into d theta plus summation of n is equal to 1 to n infinity an integral 0 to pi sin n theta sin theta into d theta. So we have 0 to pi, so we should have a standard integral which can be applied, right? So from the standard integral table, right? Standard integral table, we can write integral 0 to pi 1 plus cos theta into d theta, that is equal to pi, right? So 1 plus cos theta d theta is equal to pi. and we can again write this from the standard integral 0 to pi sin n theta, because here n is involved, right? So we will consider two cases where for n is equal to 1 and for n which is not equal to 1. So for n equal to 1, we arrive to pi by 2, and if n is not equal to 1, it will become 0. So now this equation can be written as gamma is equal to the C into V infinity, and this A naught into pi plus, considering n is equal to 1, pi by 2 into A1. So I recommend you to calculate the lift per unit span. Please calculate lift per unit span. Dash is equal to rho infinity V infinity gamma. So that can be written as rho infinity, and we have one more V infinity. So it will become V infinity square and C into pi into A naught plus pi by 2 into A1, and we have considered n is equal to 1 in this case, right? So we have L dash. One can calculate CL. So CL can be written as L dash by of rho infinity V infinity square into S. I write per unit span, so C into D, that D is equal to 1. D is the span length, right? So here rho infinity V infinity square gets cancelled, and hence we can write this directly. So rho infinity V infinity square into C. So we can write this as pi into 2 A naught plus A1 right. So that means that CL is equal to pi into 2. We already know A naught, right? What is A naught? Alpha minus 1 by pi integral 0 to pi, right? We know already A naught. Alpha minus 1 by pi integral 0 to pi dz by dx by dx into d theta naught plus 2 by pi into integral 0 to pi dz by dx cos n theta naught into d theta. So this can be written as finally CL is equal to, I take this 2 pi out and say this can be alpha plus 1 by pi integral 0 to pi d sub by dx into cos theta naught minus 1 into d theta. So we arrive to this point where the CL is equal to 2 pi, right? 2 pi into alpha plus 1 by pi integral 0 to pi x into cos theta naught minus 1 into d theta naught. So now if you calculate the lift curve slope, that is dCl by d alpha, that is equal to 2 pi. I hope you remember the expression for dCl by d alpha. Wait. So, lift curve slope, lift curve slope, that is dCl by d alpha, that is equal to 2 pi. So the similar case we have obtained in the symmetrical airfoil, right? So we have dCl by d alpha, that is equal to 2 pi. Now there may be a question: what happens if there is a symmetrical airfoil and unsymmetrical airfoil? Say in the case of unsymmetrical airfoil, you may have the lift curve slope like this. So this may be for cambered airfoil, and this may be for symmetrical airfoil. So you see, till the stalling, you have the dCl by d alpha, which is similar. But only difference is at the alpha, say alpha here L equal to 0. So alpha at L is equal to 0 is not 0 in the case of airfoil, but the alpha at L is equal to 0 is equal to 0 in the case of symmetrical airfoil, right? So after this particular stalling point, you have a flow separation. So we in general we consider the lift curve slope can, from the thin airfoil theory, can predict till the stalling point, right? So we have arrived to the CL and then dCl by d alpha, which is equal to 2 pi, right? Now we already know what is alpha L equal to 0. Alpha at L equal to 0. So alpha at L equal to 0 is the angle of attack at which the lift is equal to 0, right? So we need to calculate alpha L is equal to 0, right? So I write further equation. We can write CL, that can be written as dCl by d alpha into alpha minus alpha L equal to 0. Right? So this equation satisfies, and hence CL is equal to dCl by d alpha is 2 pi, and alpha minus alpha at L is equal to 0. So what is alpha L is equal to 0 then? Alpha at L is equal to 0 can be represented from this value. Right? So we can write this as minus 1 by pi integral 0 to pi dz by dx into cos theta naught minus 1 into d theta. So this is alpha at L is equal to 0. That is the coefficient of, the angle of attack at which the lift is equal to 0. Now, one can imagine and say, what will be the alpha L is equal to 0 for a cambered airfoil? Is it in positive or negative? From the graph, say this is the positive angle of attack, and this is negative angle of attack. So for cambered airfoil, alpha L is equal to 0 will be negative. Right? So further we need to calculate the moment. Right? I recommend you to calculate the moment. Right? And also check the center of pressure. Right? And also come to a conclusion for the aerodynamic center, center of pressure. So let me write the summary. Say the first point, the coefficient of lift is calculated by 2 pi into alpha plus 1 by pi integral 0 to pi dz by dx into cos theta naught minus 1 into d theta naught. And the dCl by d alpha, that is lift curve slope, that is equal to 2 pi. And I write the third point as aerodynamic center. The aerodynamic center is at quarter chord point. I recommend you to verify this. Then the center of pressure, which varies with CL. So verify this third and the fourth point. Like we have already derived the moment. So calculate the moment coefficient about the quarter chord point, right? And then calculate the center of pressure and come to the conclusion of the third and the fourth point. So with this information, right, I conclude the today's lecture for the cambered airfoil, right? Thank you very much.